All right, now we go to resistance. This is one of the last things that we have to do. Okay, now resistance. Now, when a battery is connected across a conductor in a closed circuit, charge carriers in the conductor will gradually move towards one end of the conductor as current flows. All right. The motion of these charge carriers through a conductor is often opposed or resisted by the conductor as they collide with one another or the atoms of the conductor. The charge carriers, when it wants to move from one end to another inside your conductor, they will either collide with themselves or they will either collide with the atoms of the conductor. So this slows them down, or their motion is being resisted. Okay. Now resistance is the measure of the opposition to current flow in an electrical circuit. Resistance is defined as the ratio of PD to current. Okay, so R is equals to V over I, where I is resistance, V is PD, I is current. Now, it is very important for you to know the differences between ratio, rate of change, and something per unit something. By now, you probably have gone through a few of these quantities. Let me just write them out for you. Now, if I give you density, this one you will tell me is mass per unit volume. Okay, this one you will tell me is mass per unit volume. Okay, now then if I give you, say, velocity, this one you will tell me is rate of change of velocity. Okay, then after that, if I give you Young's modulus, this one you will say is ratio of stress to strain. Okay, now notice the similarity in the equation form. Density is mass divided volume. Velocity is displacement divided by time. Young's modulus is stress divided by strain. Okay, equation wise they seem the same because it's something divided by something, but then when you define it, notice the pattern in which they're defined. Density was mass per unit something, whereas velocity was rate of change of something, and then Young's modulus is ratio of stress to strain. Okay, now specifically between these two, rate of change of something and ratio of something to something, this one determines how your graph is analyzed. Okay, this one will determine how you analyze your graph. Because if I tell you right now, I give you a graph of velocity versus time, sorry, displacement versus time. Say if I give you a graph of displacement versus time, and I tell you that you have a graph like this, okay, I tell you have a graph that looks like this, and then I ask you, what is the velocity at this point? What you would say is that, to find the velocity at this point, you will get the gradient of the tangent, right? So velocity here, you will say, is because it's defined as rate of change of displacement, is the gradient of the tangent of your velocity time or your displacement time graph. Sorry, maybe I better just write this in a different color. If you have a graph of displacement versus time here, because velocity is defined as rate of change of this one is not velocity, my mistake. Rate of change of displacement. Right, rate of change of displacement. Because velocity is defined as rate of change of displacement, if you have a graph like this, if I ask you what's the velocity here, because it's defined as rate of change of displacement, it will be the gradient of the tangent. Okay, V here will be gradient of tangent because it is delta S over delta T. This one here being your delta T, this one here being your delta S. Okay, So this one is if something is defined as rate of change of something, you automatically tend to relate as gradient of a tangent inside your graph. Okay, but now when it comes to resistance, resistance specifically is defined as ratio. Okay, it is not defined as rate of change of PD to current. All right, it's not defined as rate of change of PD to current. So if say you were given a graph of say velocity versus time, like the ones that's being shown here in your notes, and I tell you the variation of your velocity and current is this, and then now we ask you to find the resistance at this point, you cannot use gradient or tangent. Okay, using the gradient or tangent at that point, at this point is incorrect because it's not defined as rate of change or PD to current. It's defined instead as ratio of PD to current. What you would have to do actually is that at this point, you have to find out what is the value of, at this point specifically, you will need to find out what is the value of V. You will need to find out what's the value of I. Sorry, I write it in proper coordinate form for you. You need to find out specifically what is the value of I, what is the value of V, and then find the ratio between those two values. Okay, that is what this one is trying to tell you. This point here, you need to specifically know the value. You cannot just find the gradient or the tangent like this. This is wrong. Okay, so to find the ratio of values at this point, I said that you cannot use gradient or tangent, but there's an easy way to find the ratio value. You can use gradient, but you have to use the gradient from the origin. Okay, let me just wipe off certain stuff. You want to use gradient, you can, but don't use gradient or the tangent. You need to use gradient from origin instead to that point to find the resistance. Okay, the reason why we say that is something like this. If you look at the graph at the bottom, this one is the same PD to current graph. I again want to find out the value of resistance here. Okay, I again want to find the value of resistance here. I cannot use the gradient of the tangent, but I can use the gradient from the origin. What I mean by that is that just draw a line from the origin to that point and then find the gradient of the tangent. That one will be your ratio already. Because what we'll tell you here is that gradient from origin to that point is actually numerically equal to ratio of PD to current at that same point. Now, why do we say this? Is because if you look at this thing just now that I drew, just now I drew this thing here, right? If this one was value I, this one was value V, the resistance is the value of V divided by I to find the PD. Okay, right? This is what you see. Now, say in this diagram here, let me give some value to you. This one is 0, and then this one is I, and then this one here is V. Now, if I want to find the gradient of the origin here, if I say just by using ratio itself, R is V divided by I, the value of V that I have here divided by I. Okay, but if I use gradient from origin, notice that it will be V minus 0 and then I minus 0, which in the end gives you V over I. You notice that this one is actually the same as this. That's why I say that they are numerically equal. Okay, you finding gradient from origin is actually going to give you an answer similar to the ratio. Okay, so don't find gradient from tangent, find gradient from origin when you want to evaluate the resistance. Okay, it's because the gradient is equal numerically to the ratio. All right. Strictly speaking, when you're asked to define resistance and then they ask you to deduce from the graph how you know the resistance is changing, you shouldn't say anything about the gradient. Gradient is not the correct way to look at the resistance. It's just that here, right now, the correct way is to look at the ratio, right? But what I'm teaching you here is just another informal way of evaluating the ratio. This is by far the easiest one, but it's not a formal method to use. Okay, so don't make mention of gradient when you say you want to evaluate the resistance. Okay, so like in my case here, I can say the gradient for origin is V divided by I is essentially going to be equals to R. But there are cases where we could actually reverse your axis, I against V, current versus voltage. So in my case here, the gradient for origin is actually I divided by V, is actually the reciprocal of the resistance. Okay, so like if I see these two cases here, what can I say about how this gradient is changing? Here you can say that the gradient is dropping, right? You see it's becoming less steep. I can see that the gradient here is dropping, the resistance here is increasing. But on the other hand, if you look at the second example here, what can I say about the gradient? The gradient is dropping. Sorry. I did something wrong here. The first one, gradient is proportional to R. If gradient is dropping, R is dropping. Sorry, my mistake. And then this one here, gradient is inversely proportional to R. If I see that my gradient is dropping, my resistance is increasing. Okay. So this is how normally we evaluate whether the resistance is going to change or this is how we evaluate whether the resistance is going to increase or decrease. Just by looking at the gradient of the origin. That's the quick way, but it's not a formal way to do it. It's not accepted in your marking scheme. All right. Okay, so this one is okay. Then after that, you just move on to some of the others. Okay, now then after that, we go on to IV graphs again. All right, IV graphs again. Now, you are required to know the IV graphs, voltage current graphs for three different components: a metallic conductor, a semiconductor diode, and a filament lamp. Okay, they will often ask you to identify the IV graphs for these three components, and you're supposed to know how to draw their shapes. Okay, which is given in this page of your notes. Okay, so now you have metallic conductor at constant temperature. Now there's something called Ohm's law. Ohm's law states that current flowing through a conductor is directly proportional to the voltage across it, provided temperature remains constant. Okay, here is saying that here is saying that I is proportional to V. Okay, provided the temperature remains constant. Any conductor that behaves like this is known as an ohmic conductor. For conductor that follows Ohm's law, resistance is constant. Okay, since they say I is proportional to V, you're supposed to get a straight line that passes through the origin. And then now you want to look at the resistance. You see the gradient from the origin is always constant, so therefore resistance is constant. Okay, this is an easy way of looking at it. Now, then after that, you also have semiconductor diode. Now, a diode is just simply a device that only allows current to flow in one direction. In your case here, when it is forward bias, having positive voltage, your diode allows current to flow through relatively easily. But when your diode is reverse biased, meaning you say you have negative voltage, no current is allowed to flow. You see there's nothing here. Okay. So what do we mean by having positive voltage and negative voltage? Is something like this. This one is your diode. Okay. When you have it like this, current can flow, right? This is what we mean as forward bias. This is where you have positive voltage. Okay. Now, when you have reverse bias, you again still have the diode like this. But what is happening here is that you reverse your battery polarity. This one was positive, negative, right? Now this one you reverse it, you give it something like this. You reverse the polarity. This is negative, this is positive now. So basically you're getting positive, negative here. That's why we call this positive voltage, negative voltage. Okay. When you have negative voltage, you're basically reversing the polarity of your battery. In your case here, this is considered to be positive voltage, positive forward bias, current can flow. In this case here, reverse bias, negative voltage, no current is flowing. Okay. Now, at the positive voltages, when it's forward bias, you notice that current increases slowly and then rapidly. So this tells you that resistance decreases as current increases. Now, if you look at gradient from the origin, you can see this very easily. This point, the gradient from origin is this. This point, gradient origin is like this. This point, gradient from origin is like this. The gradient from origin is increasing, so therefore your resistance is decreasing. Because here you see gradient from origin is I over V, is 1 over R. So gradient is inversely proportional to R. If your gradient increase, your resistance drops. Okay, so this is one way to look at it. Now then the last one you will need to know is filament lamp. Okay, for filament lamp is this one. Okay, so let me just clear off everything again. Okay, now for filament lamp, at small voltages, the graph is usually a straight line. Okay. At small voltages, the graph is straight as resistance remains constant. So it's actually straight initially. But then when you go towards higher voltages, the line will start to curve, like what you're seeing here. Now, the reason why it starts to curve is because when your current increase, your filament lamp will heat up. Because you know that when you run current through a metal, like tungsten wire that is used to make filament lamp, it will heat up. So when it heats up, it will have an increase in temperature. Okay, when you run current through it, your metal wire heats up, you have an increase in temperature. Now, the increase in temperature causes the filament atoms to vibrate more rigorously. So it will oppose the flow of any charges. Just now when we talk about resistance, we mentioned that when your charge tries to flow inside a conductor, it's opposed by the atoms of the conductor itself. So specifically now, your conductor is the filament lamp metal. The atoms are vibrating more rigorously, so it's opposing the flow of your charges. Your current will actually get less, therefore resistance has increased. Your filament lamp heats up, the atoms vibrate more, you have more resistance to your current flow, resistance would have increased. So another thing you can also do here is to look at gradient from origin again to identify this. Over here is gradient from origin equals to I over V, 1 over R. So gradient is inversely proportional to R. So again, you try to see the gradient. This one like this. this one like this one like this, you notice that the gradient is dropping, so resistance is increasing. Okay, so resistance increases as current increases for filament lamp. Okay, so filament lamp resistance increase, semiconductor diode resistance decrease, ohmic conductor or rather metallic conductor at constant temperature, resistance is constant. You need to know these graph shapes if you're asked to produce it, reproduce it. All right, and you need to know how to deduce whether the resistance is increasing or decreasing from that graph shape. Okay, so that one is okay. Then we go on to some other stuff. Okay, now this one is talking about resistors also. Now you have two special kind of resistors inside your syllabus. You actually learned this in A2 last time, but then they've actually decided to add it inside your AS again. So now you have something called thermistors and light dependent resistors. All right. So both are resistors. All right, but these resistors have resistance that change with certain things. The first one is thermistor. Okay. A thermistor is just a temperature-dependent resistor that changes resistance with temperature. Now, for a negative temperature coefficient thermistor, resistance decrease as temperature increase, which is why you get a graph shape that looks like this. You notice that as temperature increase, resistance drop. Okay. Your syllabus will only deal with negative temperature coefficient thermistors, meaning you say you only deal with graphs like this, where temperature increase, resistance drop. Okay. Now, change in thermistor resistance with the temperature is not linear but exponential. When your thermistor is heated, it tends to conduct more current. The reason why is because as temperature increase, the thermistor will make available more free electrons to carry current, thus its resistance decrease. You can just think of it this way. The more free electrons released because heat energy is absorbed. Okay, more free electrons release because energy is absorbed. Okay, so this is for thermistor. Now, you also have something called light dependent resistors. Okay, so light dependent resistor again is a resistor that changes its resistance with something, but here it changes its resistance with light. Okay, so a light dependent resistor changes resistance with light intensity, with brightness. In complete darkness, it has a very high resistance of 10 mega ohm. In bright sunlight, its resistance will fall to 100 ohms. Okay, so basically you have a graph of resistance versus light intensity or brightness now. All right, when brightness increase, resistance drop. Okay, the change in resistance with intensity is not linear but exponential. That's why you get a graph shape like this. When light intensity increase, your LDR conducts more current. The reason again is somewhat similar to thermistor. When light intensity increase, your LDR absorbs more photons of light to enable more free electrons to carry current. Therefore, resistance decrease. Therefore, you can carry more current. This is for LDR. Okay, so that one is all right. Then I finally go to the last page. Okay, now this one is probably new. You probably haven't seen this in IGCSE before. Just as we learned the concept of resistance, we also have something called resistivity given by the symbol rho. The symbol rho here is the same as density, but here in the electricity chapter is used to denote resistivity. Okay. Now, if you have a given conductor with a certain resistance, what we'll say here is that the resistance of a conductor at a given temperature depends on a few factors. It depends on number one, the length L of the conductor, which is parallel to current flow. The what we'll say here is that resistance is actually directly proportional to length. The longer your conductor, the more resistance you encounter. And then the second thing you can say is that resistance is actually dependent on cross-sectional area, which is this one here. This one is your cross-sectional area A. Okay, your cross-sectional area A is perpendicular to current flow. Okay, so what can you say about resistance and cross-sectional area? You can say that resistance is inversely proportional to current. Hey, wait, resistance is inversely proportional to length, sorry. Okay, there's something wrong with what I wrote here. Okay, sorry, now I just realized it. Resistance is inversely proportional to cross-sectional area 1 over A. Sorry, I noticed that there's a mistake here. Resistance is inversely proportional to cross-sectional area. So what you can say here is that when your area drops, your resistance ought to increase. When your area increase, your resistance drop. That's why we say that it's inversely proportional to cross-sectional area. Okay, so these two factors affect resistance, length and cross-sectional area. Another thing that could also affect resistance is the material type that contains the mobile charge carriers. All right, there's a particular physical quantity that relates to this, right? But to get that, you have to relate these two other parameters together. So just now we say that R is proportional to L and R is inversely proportional to A. If you combine those two relations together, you will get R is proportional to L over A. You want to get rid of the proportionality sign, you introduce a constant rho. Then you get R is equals to rho L over A, where rho is the resistivity measured in ohm meter. It's a measure of the resistance of the material. Okay, and then this one is good. It's a better measure of your resistance because it's constant for any given material type, regardless of its size and shape. It's something like Young's modulus. If you've done deformation of solids before this, we will tell you that Young's modulus is a measure of stiffness of the material. And it's a better measure of stiffness because it just depends on the material. It doesn't depend on its size and shape. So it's a similar analogy here. Resistivity gives you a measure of the resistance. And it just depends on your material. It doesn't depend on the size and shape. Right? So this is resistivity. Okay, then I'll fill all. Then we go to the last part, power. Okay, power should be very fast. Now, power, you know, is rate of work done or rate of energy change. So in an electrical circuit, electrical power is the rate at which electrical energy is converted into other forms of energy. So there are three equations that you need to know for power. Electrical power P over device is P equals to VI. Okay. And then since you know that resistance is R equals to VI from the previous page, I is therefore V over R, or V is equals to IR. Now, if you substitute for, if you look at this equation, equation 1, if you substitute for V, you get PI times IR, giving you PI square R. And then after that, if you again refer to equation 1, now you substitute for I, you get P equals to V over R times V, you get V squared over R. These three equations will be used normally to calculate power dissipated in an electronic component like your resistor or your lamp. Okay. Now, specifically for a cell or a battery, the power generated can be found through a similar equation, in 1, where instead of using P equals to VI, we use P equals to EI, where E is the EMF. The equation 1 that you have here is using V, PD. This equation here is using E, EMF. Okay, and I is the current through the cell. And then eventually what we can also tell you is that because of conservation of energy in an electrical circuit, power generated at the cell is equals to total power dissipated at resistors. Okay, so that is for this.